Well, we really appreciate everyone joining us this morning for Flex Train, a training opportunity brought to you by Johnstone Supply. So this is my absolute favorite topic when it comes to HVAC. I mean, I love talking about the vapor compression cycle for refrigeration, but flame rectification is the #1 topic that is so misunderstood in our industry. When we introduced flame rectification, we failed to educate the industry on what we were actually doing with flame rectification, because we had did the same thing for decades, and all of a sudden we came out with some new technology and we just went, hey, here's the technology. And we never said, hey, here's the technology and it is so different than what you're used to working with. So let us train you and you can understand it. We didn't do that. We just said, hey, here's some new technology. So what has happened over time is we have formulated our own opinions based on miseducated judgments from previous technicians who were taught a different style of learning for what we do for monitoring flames in our combustion process. So we're going to spend a little bit of time this morning talking about flame rectification and what it actually is, not the misconceptions, but what it truly is. So if we look at what we've done with flames to be able to give our equipment an understanding of what's going on, whether we have completed combustion or not, we have to look back about where it all came from. So it actually goes back a pretty long time. If we go back into the early 1800s, 1821, a German physicist named Thomas Johann Seebeck, he discovered that if he could take two different metals and join them at the ends and put a separation at the opposite side, and then he could introduce flame to that. At that time, it was just candle power, right? It was just an oil candle. He found that by introducing heat to that, which is now what we would consider a bimetal contact, by applying heat to those opposing ends, the dissimilar metals could actually create a magnetic field. So we now know that as a thermoelectric current, and it's thermomagnetism, but in that days it was just an interesting change in how things operated. So he did that by placing if you look at how they designed that original one, so he placed a polarized rod, which was basically a compass, inside of that armature, and when he applied heat to it, the dissimilar metals produced a thermoelectric effect which caused the needle to move. Right? It shifted the direction. So it was an indicator that we had a magnetic field, because our indicator was magnetized, it was a polarized piece of metal. So it shifted the magnetic pole in that field. Well, later we were able to realize that in that process, anytime we can introduce a magnetic field, we can excite electrons and we can create a magnetic flow of electrons, which we can measure in voltage, right? So that voltage is the pressure of the movement of our electrons. Just like we apply pressure to water molecules to push them through a pipe, we apply pressure to our electrons to move them in a direction through a field or through a wire, whatever it is. But that is our pressure. So as we applied our heat, it converted our energy into a pressure, which is our voltage. So we were able to produce a very, very slight voltage by applying heat to our bimetals that were joined at an opposing end. So we took that principle and we applied it into our early pieces of flame recognition, is what we did with that. We were recognizing that there was a flame there by the effect that it had on creating some voltage. So we put that application into a device using that exact same principle, where we had a bielectric connection, a bimetallic connection. And when that bimetallic connection was heated, it produced a magnetic field, which in turn could be used as a supply of electrons, a supply of voltage. Very, very small though, but it was actually producing voltage. So we put that in the form of a thermocouple, and we used that principle for decades. It was a very simple solution to our issue, because most of our controls were actuated mechanically. You know, we weren't using a lot of electronics in our early heating appliances. We had very little electrical controls. I mean, we would have a switch to bring on our gas valve, which was our thermostat, and then we would have a fan switch that would bring on our blower to turn our blower on. But besides that, really, we didn't use a lot of controls. We used a thermocouple to hold our gas valve in. So what we did with that thermocouple is we just created voltage to hold a solenoid. And we found that if we needed more voltage, we just applied more thermocouples. And we put them in a series circuit so that we can increase the voltage. Because if we think about electrical, if we put something in a parallel circuit, we're going to maintain our pressure, we're just going to increase our current. If we put that in a series circuit, we're going to increase our pressure, our voltage. So if we needed more voltage to hold in our solenoid, say we had a larger solenoid that needed more power to hold it, it needed a larger magnetic field, we simply increase the voltage by adding more thermocouples together. And then we would put them in one housing, and we called it a thermo pile or a power pile generator. And we use that technology forever. It's very predictable. In that entire effect, we could actually calculate how much voltage was being produced by a thermocouple to know how many of them we needed to put together to make our thermopile. So depending on the type of thermocouple, we could look at specific voltages that it would produce at desired temperatures. So we know that most of our combustion process for natural gas, even in LP, we're somewhere in that 3,500, 3,300, 3,500, 3,600 degree Fahrenheit range for our combustion process. So we're going to work with that C-type thermocouple. A lot of the other thermocouples won't go that high. You know, a lot of us are familiar with the K-type thermocouple, right? That's ones that we still use today in our digital multimeters. That's the K one. It's only good for 2,500 Fahrenheit. Most of the time, I'm not working on something 2,500 degrees Fahrenheit with my thermocouple. It's got plastic tips and handles and leads on it, right? But I can do that with my C-type, my thermocouple that I use for furnaces and for boilers and most of our heating appliances. So at 3,500 degrees Fahrenheit, I can produce 30 millivolts with that C-style thermocouple. And if we look at our packages, they actually tell us how much they generate. So the next time that you're looking at a thermocouple, just out of curiosity, take a look and see what it produces. If we look at the Honeywell, that Q340 series, I mean, those things have been around for decades. I don't know how many thousands of those I've put on in my lifetime. When I was doing service for residential HVAC, part of our service program was if it had a thermocouple on that piece of equipment, it got a new thermocouple because they were that inexpensive. So we included it as our service plan. So there were a lot of furnaces out there that got new thermocouples every year because it was an inexpensive component that served a critical part of the sequence of operation. So if we look at a standard thermocouple, 30 millivolts, right? So we take that same philosophy and we need to hold a larger valve open, one that has a larger solenoid on the gas valve. We simply increase the amount of thermocouples that were inside of that so that it now is a thermopile that can produce more voltage. So with that typical thermopile, if we look at that, that Honeywell, that is a Q313, that one produces 750 millivolts. So typically in the residential world, we're working with gas valves that are moving under 200,000 BTUs. So we're typically on a gas valve that 30 millivolts is sufficient to hold that valve open. If we're talking about larger commercial and industrial gas valves, they have much larger bodies, they move more volume, which means they need more pressure to hold the valve open. So it has a larger coil, larger solenoid, so it needs more voltage. So we use a power pile, which can generate 750 millivolts. So it generates that voltage to do work, okay? So if we look at a gas valve, as we're trying to light it, as we're trying to establish its control, we're going to, on the button, the gas valve button, we're going to apply pressure on that, which is going to push the plunger down. It's going to allow gas to pass through our pilot. It's going to warm up our thermocouple. Our thermocouple is going to generate a voltage that is going to energize a winding that is going to hold that plunger open. That's going to allow that valve to operate. As it continues to move, it is now just simply going to pull pressure while the pilot light is operating, and it's going to hold that valve open. So that if there was some interruption, if I have a backdraft of flue and it is enough air that it blows out my flame, I'm going to stop producing voltage on my thermocouple or my thermopile, however you prefer to call it, and it is going to release the solenoid on my plunger and allow my plunger to close and shut off the gas supply, and that is my safety control on a gas valve. And that's what we used forever. So we got used to using that principle. Then as the equipment changed in its efficiency and as electronics developed, we moved into an entirely different platform. We moved into a platform called voltage rectifying. So we're not voltage generating anymore. We're voltage rectifying, and we're doing that through our electrical circuit, but we're using the assistance of the flame. So what was found was that as technology was moving and as electronics are developing, we found that we could produce this phenomenon called rectification across the flame. So as a flame is burning, it has positive and negative ions across it. So it develops a path of flow for electrons, but it also can break up that flow of electrons. It can create a barrier for our electrons to flow through. So if we think about AC voltage has a nice, clean, smooth sine wave because it's being produced by a generator that's turning, at a consistent revolution. So our sine wave is moving very smoothly. Well, if we were to take AC voltage and we used a diode, which a diode is it's like a limiter or a choke, so that we can control our electrons and only allow them to flow one way and only allow a certain amount. With different diodes, we can only allow a certain amount to pass through that gate. So if we use a diode in an electrical circuit, we can cap off how much electrons can pass through. We can make sure that they only flow in one direction. And then if we use resistors, we can actually act like a load on a circuit. So we do that a lot for voltage rectification. So if we are converting AC to DC voltage, that's all we're doing. We're going to take an incoming AC current. We are going to grab my Sharpie. We're going to take an incoming AC current. We're going to allow one side of that, one path for those electrons to flow through a constant resistance. And then we're going to allow a separate path of electrons to flow through a different resistance and then hit a diode, which is now going to chop those up for us, right? So if I have a solid and I have a chopped, looks a little bit like DC, doesn't it? It is. It's not true DC, but it is rectified AC so that it looks like DC. So the interesting effect of flame rectification is as our electrons move across a flame, they don't have a constant path. Remember, in that combustion process, we have a lot of carbon molecules that's passing through our flame still, right? Even through complete combustion, we have carbon molecules. And we have moisture that is now being condensed out of the air. As our electrons try to pass through that flame, they are conductive across the flame because of our carbon molecules. Carbon is a conductor of electricity. So we actually allow our electrons to try to make their way back to ground through the flame. And in that process, we're actually creating a load on the flame as it's making its way to ground. That was never taught when we moved into flame rectification. What we are doing in flame rectification is exactly that. We are going to now use a hot surface igniter most of the time. Sometimes we'll use a spark to pilot system, but eventually we're doing the same thing. We're going to allow a combustion point We're going to add fuel, which is going to allow our flames to pass across our complete burner assembly. We are going to now apply electrons directly into that flame. So we're going to use an orange wire. Most manufacturers use an orange wire for their flame sensor. It's not a sensor, it's a rod. That's all it is a rod. We are going to apply electrons into that flame, and we're going to add a dedicated ground onto that circuit. And we are going to pass electrons from our control board through the flame back through ground. That orange wire has high voltage on it. It's not a sensor. It has applied high voltage, typically between 50 and 80 volts AC, depending on the manufacturer of the control. You can take your meter and you walk right over to it, and you can go straight from ground to the tip of your flame rod, and you have AC voltage. So we apply electrons into the flame. As those electrons are passing through that flame to ground, they get chopped up. The AC sine wave gets chopped up and it looks like a DC voltage now. It doesn't look like an AC voltage. The clean sine wave is gone and it's been chopped up. So we create a DC current that is passing through that flame. And because we have applied a load onto those carbon molecules, we actually have current passing through there. So we now create a load in amps on DC voltage, and we read it as microamps DC. But it is absolutely applied AC voltage. I encourage you the next time you're working on a gas furnace to walk over with your multimeter, put it on AC voltage, and check from ground to your flame rod, and you're going to find something that you never anticipated to be there, because we weren't taught that. That's why I love doing these classes. I love going through the simple fundamentals of what we do, because a lot of the fundamentals we're never really taught. We may have been told the science of it, but we didn't talk about exactly what it's doing. And that's what we do in flame rectification. We take AC voltage, we convert it to DC. So I prove that in my classes. So what I have done is I have calculated out the values that we would need for our resistance and the peak applied DC voltages that are peak applied current that we want flowing, our electrons that are going to flow through the diode. And I create an electrical simulation for that so that I can apply a 1.5 microamp DC load onto my flame rod from ground. I looked at applying for a patent on it. It's very expensive, and I wouldn't really sell enough of them. But if you as educators have a piece of equipment in your lab that you don't want to hook gas up to, no big deal. We can simply do that with flame rectification. Or if we're out in the field and we're to verify the actual trip point of a control board, we can set that at. Most of them trip about 1 microamp typically, but they're all over the place depending on the manufacturer. I've seen them go down as low as 0.17 on some of these commercial applications. So all I'm going to show is that I don't need flame anymore to hold my control circuit. I need flame rectification or AC to DC voltage with a load on my flame. So the resistors will be the load, the diode will be the rectification circuit converting my AC to DC, and with knowing those specific values, it just takes a little bit of math calculations and it can be found. It took me about 2 weeks or so. It took a little time to plug numbers in, but it worked. So after ignition of the hot surface igniter, in the safety time period after my gas valve comes on, I immediately apply my rectification circuit, which is a 1.5 microamp DC load from ground to the tip of the flame rod. And I have a happy circuit board. I just brought on my fan and I have no error codes. My circuit is complete. It believes that I have flame because I have created flame rectification. So we measure that. I'm glad you're on here, Paul. Does that picture look familiar?
Yes, it does.
That would be Paul Grimm's creation on the right-hand side. And it is the most perfect example of what we do with measuring flame rectification. If we look on the wiring diagram, so on the left is a wiring diagram off from a Goodman furnace. And if we look at that, simply looking at the wiring diagram, we can prove the philosophy. My flame sensor that is being called, which is just a flame rod, is on the 115 volt side of my circuit. It's on the high side of my transformer. It is in the exact same power supply as my hot surface igniter, my induced draft blower, and my circulating blower. So it is 100% on the high side of my circuit. We apply current to that wire. If we break that wire, just unplug it from the flame rod, and we put our meter in series with that, and we put it on microamp DC setting, we will see that we will have above 1 microamp DC or greater on most control boards. Typically, that's going to be significantly higher, even up to 10 or so. 1 is typically the trip point on most of the Honeywells that I encounter.
Okay, throw something in here.
Please do.
I actually do see some manufacturers that do go up to 120 volt AC on that. So
I have seen a couple. Yeah, it really trips guys out when I get a high voltage one from like a White Rogers. And they go 120 volts. I'm like, yes, complete AC voltage on that circuit. So that's what we do. We convert AC to DC as it passes through the flame. We apply electrons onto the carbon and the moisture molecules so that there is a load, and we can measure that load, just like we measure the load on a light bulb, except now we're going to be in microamps, and we can measure how much that load is. And that will verify how much the electrons are flowing through there. So when we look at the construction of a flame sensor, we would expect to be very complicated and it's doing a lot of work. It's not. It's made of Kenthal. So Kenthal is a trademark for a family of iron, chromium, aluminum alloys. The reason we use it over stainless steel, the original ones were out of stainless steel. The reason we use Kenthal is it has a slightly higher temperature rating than our stainless steel counterparts. It can withstand a few hundred more degrees. So we take a Kenthal rod and we insulate it with a little piece of ceramic, and we put it on a standard steel plate, and then we attach a screw so that we can anchor it. But in most manufacturing processes, it is simply a piece of steel, Kenthal steel, a ceramic insulator, and a plate, which is why they're only typically a few dollars. They're not very expensive. They can withstand up to 1800 degrees Fahrenheit of direct contact. So we do need to clean those because they're not rated for 3500 degrees Fahrenheit. We do get some oxidation on those because they're trying, it's the metal's trying to protect itself from destruction, so it will oxidize on the surface, and then we need to actually clean those. So part of our maintenance procedure is to clean that flame rod or flame sensor to remove oxidation off from it. We have to move the surface that is actually burnt because it's not rated to withstand 3500 degrees of combustion. It's rated for 1800 degrees of combustion. So we clean that.
And anything that's coated on there too is going to act as an electrical insulator. So any kind of insulation is going to stop the flow of those electrons that we need.
It's all about the flow of electrons. If I add an insulator to a conductor, I'm going to slow down my flow of electrons. So if we look at that again, the next time that you are working on a furnace and you're doing a service and you're cleaning that flame rod and you're making sure that it's nice and clean so that it can be a sensor for our flame, just remember it's one of two important parts in that entire circuit. The next time you look at a furnace, you're going to see it differently. You're going to see two components to this circuit, and it'll be the same way in every hot surface ignition gas-fired appliance that you will ever encounter. You're going to see an isolated flame rod and a dedicated ground wire. And that dedicated ground wire goes directly back to the control board. It doesn't stop anywhere. It goes directly from the burner box surface to the ignition control board. That is the circuit that is completing our electron flow for our heat verification, our flame verification, our rectification circuit. So it is as important to make sure that you have proper ground on that circuit as it is to have a clean flame rod. And in a lot of applications, that burner box is sitting underneath of a draft inducer. If we're talking about an upflow 80% or even a 90%, a lot of times our draft inducer is going to be sitting above our burner box. and we get leaks in our seals because we have a lot of expansion and contraction going on between dissimilar metals. Typically, we got our ABS draft inducer or our steel draft inducer sitting up against a galvanized or a standard steel collector box with a gasket in between, and we get some expansion and contractions. So we do get some condensation sometimes leaking out of those. Very acidic condensation that will absolutely create corrosion on that burner box. How many times have we seen a burner box that's got a rusted top plate to it, right? What's rust? It's an insulator. So we need to make sure when we're cleaning these flame rods, we're also inspecting that ground wire, removing that screw, rubbing it down with a little bit of sandcloth or wire, putting that back in and making sure to measure our microamps. Because we had not very long ago, had a contractor in one of our other states. He put 5 boards on a furnace, all under warranty. Went, hey, what's going on with this? I said, well, let's take the board and let's go check it out. So I've got an 80% Goodman furnace. I just ripped it all down, used all the factory wiring, put it on a broken AC pad that we had. And so that's my demo, right? That's a not fully operating furnace. We put the last control board we replaced on, everything worked right. I said, man, what's going on? I said, you got a bad ground. You have either a bad ground at the connection on the burner box, or you got a bad ground for your furnace, because we rely on that path of ground to flow our electrons. So that is it. That's what we do with flame rectification. So to duplicate that, I simply have my own calculations for my resistance and for my diode values, and I pre-built my own flame rectification. For you that are trainers, that have equipment in your shops that you would like for those things to operate so that you can demo full, complete combustion cycles, let me know. I got 100 or so of them already pre-packaged with instructions on how they actually operate. So it's very easy to understand flame rectification when we know what's going on. We're not generating voltage like we used to with a thermocouple or power pile. We are simply applying voltage. We are rectifying it as we pass across the flame on our way back to ground. And that is modern flame rectification.
I had another thought too, just on the service side of it. If you guys are ever going across or coming across a building that's got lots of flame rectification issues, and you're going in there and cleaning that flame sensor, often anything that's going to insulate that flame rod is going to stop this flow of electrons. So I have found on quite a few times that on single pipe systems and furnaces where it's bringing the combustion air in from the mechanical room, a lot of times any kind of chemicals or dust or anything, your salt bags for your water softener, any kind of chemicals that are brought into the combustion process through the intake will coat that flame sensor, and you'll have environmental issues like that are causing you to clean that flame rod more often than you should. So be aware of the environment around what's being brought into the combustion process too, because it actually will bake those chemicals onto that flame rod.
Onto it. The laundry room is the worst place to install a furnace.
Yep.
Plain and simple, because of the additional chemicals that we have in our atmosphere. They will need to be cleaned a lot more often. It's good stuff. All right, well, I appreciate everybody joining us. Thank you so much for being a part of the Flex Train program. And here at Johnstone Supply, we are so grateful to have you with us. Everybody have a safe day and a happy Halloween coming up.